Calculating pH of aqueous solutions using the hydroxide concentration. Acids and bases react with water differently. Acids react with water to form the H3O+ ion, or hydronium ion, in the acid's conjugate base. In this situation, we would simply take the negative log of the concentration of hydronium ion to find the pH. However, bases react with water to form the hydroxide ion, or OH-, in the base's conjugate acid. Notice that this reaction does not contain H3O+ as either a reactant or a product. So how would one go about calculating the pH of a solution that seemingly has no H3O+? To answer this question, we first need to explore some important relationships. Most acidic and basic solutions have water as the solvent. Not only can water react with what's being put into it, but it can also react with itself. One water reacts with another to form H3O+, or the hydronium ion, and OH-, or the hydroxide ion. This reaction is known as the autoionization of water. The Kw, or autoionization constant, is the equilibrium constant for the reaction that we've just discovered. If we were to set up the equilibrium expression for this reaction, we would see that the Kw is equal to the concentration of hydronium multiplied by the concentration of hydroxide. Using this equation, we can find out some pretty important information. In pure water at 25 degrees Celsius, the Kw is equal to 1.00 times 10 to the negative 14. By replacing the Kw with the other side of the equation, we see that the concentration of hydronium multiplied by the concentration of hydroxide is also equal to 1.00 times 10 to the negative 14. Pure water is considered neutral, and neutral solutions have equal concentrations of hydronium and hydroxide. So by taking the square root of 1.00 times 10 to the negative 14, we can find their true concentrations. In pure water at 25 degrees Celsius, the concentration of hydronium and the concentration of hydroxide are both equal to 1.00 times 10 to the negative 7th molar. Some important notes to be aware of. No matter what the source of hydronium or hydroxide, acid, base, or water, these two ions exist together, and their concentrations are dependent on one another. This is how we can calculate the pH of a solution that seemingly has no H3O+. If there are hydronium ions present, there must be hydroxide ions, and if there are hydroxide ions, there must be hydronium ions. Let's look at an example. If a solution has a concentration of hydroxide equal to 1.00 times 10 to the negative 4 molar at 25 degrees Celsius, the concentration of hydronium can be determined from the relationship we just established. We know that the Kw is equal to the concentration of hydronium multiplied by the concentration of hydroxide. And we also know that at 25 degrees Celsius, the Kw is equal to 1.00 times 10 to the negative 14. We've been given that the concentration of hydroxide is equal to 1.00 times 10 to the negative 4 molar. Now let's set up our equation. All we have left to do is to divide both sides by 1.00 times 10 to the negative 4. That gives us an H3O+ concentration of 1.00 times 10 to the negative 10th molar. Now let's find the pH. The pH is equal to the negative log of 1.00 times 10 to the negative 10. So our pH is equal to 10. Just to recap, the Kw is equal to the concentration of hydronium multiplied by the concentration of hydroxide. To calculate pH, we have to take the negative log of the concentration of hydronium. That's because the P of anything is equal to the negative log of that same anything. So if we were to take the negative log of the concentration of hydroxide, we'd get the POH. We already established that the Kw is equal to the concentration of hydronium multiplied by the concentration of hydroxide. And at 25 degrees Celsius, the Kw is equal to 1.00 times 10 to the negative 14. We also know that by taking the negative log of the concentration of hydronium or the concentration of hydroxide, we get the pH or POH respectively. Now let's derive another equation. Let's start with the equation at the top of the screen. We're then going to take the negative log of both sides of the equation. Using our properties of logarithms, we can separate the two terms on the right side of the equation to get the following. Now it seems that the right side of our equation looks awfully familiar. Let's go ahead and substitute pH and pOH. So our new equation becomes 14 is equal to the pH plus the pOH. Let's do another example. We just derived that 14 is equal to the pH plus the pOH. If we know that our hydroxide concentration is equal to 3.76 times 10 to the negative 5th molar, we're first going to calculate the pOH. So we're going to take the negative log of 3.76 times 10 to the negative 5th, and that's equal to 4.425. So our pOH is equal to 4.425. So let's set up our equation like above. We have 14 equal to pH plus 4.425. Now all we have to do is subtract the pOH from both sides of the equation, and we'll be left with the pH. So our pH is equal to 9.575. Now let's practice. Pause the video and give these problems a try. Now let's use a real example. You've just made a solution at 25 degrees Celsius of 0.0657 molar potassium hydroxide, or KOH. KOH is a strong base, and strong bases completely dissociate, which means when placed in water, it separates into its respective ions, which include the potassium ion and the hydroxide ion. Since it's a one-to-one relationship, the original concentration of potassium hydroxide is equal to the final concentration of hydroxide ion. You now have two options to calculate pH from here. Either 14 equals pH plus pOH, or Kw equals the concentration of hydronium multiplied by the concentration of hydroxide. Pick one and calculate the pH for yourself. The answer is that the pH equals 12.818.